We've seen that formal definition of convergence. It's worth also thinking about what its negation looks like. What would be the definition for non-convergence? So when will this definition fail to hold? Well, it fails to hold. I won't spend too long on this before we get on to some of the proofs. The definition fails to hold, so we can say the sequence does not converge to the limit L. What does that mean? That means that, and you have to turn the original definition around. So the original definition for convergence said for every epsilon you can find an n. For every epsilon you can find a capital N with some property. So the definition for non-convergence will be the opposite of that. Not for every epsilon you can find an n. Now the opposite of that must be, well, there exists at least one epsilon for which there is no n. No. The original property says for every epsilon there exists an n. The opposite of that is, well, there's at least one epsilon for which there is no n. So here it is. You say the sequence does not converge to the limit L if there exists some epsilon greater than 0, such that for every positive integer, this inequality xn minus L less than epsilon will be broken sometimes. So there exists some epsilon greater than 0. There's some narrow distance you can put around this claimed limit L. And no matter how far out in the sequence you look, there'll always be sequence elements that don't lie in that interval. So that's the way to think about non-convergence. Okay. So you need to mull over and think about that definition of convergence, roll it around in your mind a bit, compare it to some convergence sequences that you already know about, some of the simple sequences, 1 over n, 1 over n squared, etc., and see if you can get to grips with it. Okay? What will also help us to get to grips with it and see how it's working is to look at how we can use that formal definition of convergence to prove some of the properties of convergence. Okay? And that's why we need the formal definition of convergence to allow us to construct these rigorous arguments. Okay? So the first one we're going to look at is theorem 1.1, which says that you've got the statement of it there on the board. If the sequence converges, then its limit is unique. Now, how do we prove this? Well, we'll prove this using proof by contradiction. You may have heard of this proof method before. How does a proof by contradiction work? Proof by contradiction works by you first, so you have a statement which you're trying to prove. What you do is you assume that it's actually false. So you make a working assumption that the thing you're trying to prove is false. So you assume it's false, but then you derive from that, or you show how that assumption leads to something nonsensical, leads to a contradiction, which means it can't be false. There aren't contradictions in the mathematical world. There aren't contradictions in the mathematical world. Or if there are, we're in trouble. Yeah? So we assume what we're trying to prove is false, and from that assumption we derive a piece of nonsense, something which is clearly false. And that then forces us to conclude that our original assumption was wrong, and so the theorem must be true. Okay? So we assume there is a convergent sequence. There is a convergent sequence with two limits, at least two limits. Remember, the theorem is saying a convergent sequence can only have one and only one. Okay. So we'll let AN be our sequence, and we'll let an converge to A and an converge to B as n goes to infinity, and assume that A is not the same as B. So we assume that the two limits are different. Now, a sketch can help you think about this. If A and B are different, well, we talked before how, well, what if the two supposed limits were really close together? Maybe then the convergence sequence could get closer and closer to both of them simultaneously. Well, no matter how close together they are, if you choose it, we can choose an appropriate zoom factor, if you like, so that we can separate them on the number. As long as they're not the same number, we zoom in to the number line by an appropriate amount, we can see them as separate points and think about them as separate points diagrammatically. Now, we've given ourselves the assumption that the sequence is convergent towards A and towards B. So that means we can work with the formal definition of convergence. And we're going to use an epsilon value of 1/3. So 1/3 is going to be this radius, the radius of. So I'm going to be thinking about the point A plus 1/3, A minus 1/3, and B minus 1/3, and B plus 1/3. Now, there's nothing amazingly special about the quantity of 1/3. Many quantities we do here, but all I want to do is choose a radius. Sorry, that's okay. I'll fix this by saying C. So I want to let C be the distance between A and B. Because A and B are different, there's a non-zero distance between them. That's that quantity C. And then the intervals I'm going to talk about are the ones with radius 1/3 of C. And the only special thing about 1/3 of C is that it's chosen so that the two intervals will not overlap. Okay? We set this radius to be 1/3 of the distance between A and B, and the two intervals will not overlap. Okay? Now, since the sequence AN converges to A, we know that there exists N1 such that, so what I'm doing here is I'm using the definition of convergence. So there exists a capital N1 such that if N is greater than or equal to N1, then the distance between AN and its limit A is strictly less than 1/3 of C. Okay, so I'm using epsilon in the definition to be 1/3 of C. What that means is from some point on, when you're after the position capital N1, the sequence has to be wholly contained within this interval on the left. But also, since this sequence AN is converging to B, I know that there exists a point N2 such that if N is greater than or equal to N2, then the distance between AN and the other limit B also has to be less than 1/3 C. Okay? So both of these statements, the existence of N1 and N2 comes from the definition of convergence. The existence of N1 and N2 comes from definition 1.6. So we're nearly at the contradiction now. We pretty much are. We just want to draw the conclusion in a nice way. My first statement there, this first statement here says from some point, the sequence has to be all of it contained within this interval over here. The second statement says, well, from another point on, the sequence has to be wholly contained with this interval over here. Now, those two statements are incompatible because the two intervals have no intersection. They're completely separate. So it's wrong to say something is over here while simultaneously it's over here. They're two completely separate locations. But I just have to hammer it home a bit because the two statements, they're talking about two different points. So as long as I choose, if I let n now just be the maximum of my n1 and n2. So I know after the point n1, the sequence is on the left. After the point n2, the sequence is on the right. Well, I can't tell which of n1 and n2 is the greater, but they're just two numbers. So as long as what I can say now is from the point capital N, now I can say this. Now it says the sequence is simultaneously on the left interval and on the right, and that's impossible. So we let n be the maximum n1 and n2, and from the above, if n is greater than or equal to this value, capital N, then the absolute value of xn minus a must be less than a third c, and the absolute value of xn minus b must be less than a third c. This is impossible. It's a contradiction as the two intervals do not overlap. Oops, see that? As the two intervals, well, I'll use the set theory language. The two intervals have no intersection. Their intersection is empty. So you can't have something that's in an empty section. That's what this statement here is seeming to say. If n is bigger than or equal to this capital N, is the maximum of n1 and n2, it's saying the sequence element xn is in an empty set. That's the empty sets, of course, being the intersection between the two intervals. But as you can see, because of the way we've chosen the radius of the intervals, they can't have any intersection. We've chosen the radius to be a third of the distance. Okay, so we've reached a contradiction. Of course, as we discussed there, we can't have a contradiction in maths. We can't prove something true that we know to be false. So there must be a problem in our argument that led to this. But if you check all the steps in the argument, and this is how proof by contradiction works, you check all the steps in the argument, everything is fine. I haven't misspoken, except for at the very top, when I said, well, assume we've got a sequence which has two different elements. Everything after that was perfectly fine and mathematical and rigorous, but that statement in itself, there must be a problem, okay? Because that's where the whole thing started. So it must be that this assumption is false. So there can't be a convergent sequence with more than one limit. That's the conclusion. So this is impossible. This is a contradiction. So we conclude that our original assumption is false. Our original assumption is false. And that is, sequence limits are unique. Sequence has a limit. That's the only limit it has. Can't have two separate limits. Okay? So that's a nice illustration of using the formal definition of convergence to produce a strict, rigorous argument for one of the properties of convergence. And that will lie behind, kind of everything that we talk about convergent sequences from now on, because now we know that we can talk about the limit of the convergent sequence, not just a limit. We now know for sure that there is a limit, there's only, so we can speak of the limit of the convergent sequence without, and we know that we're on firm mathematical ground. Is that okay? Any questions or things you'd like me to clarify about the proof, or any queries you have about it? I'll get these visualizer pages up on to the comments to the video as well. Let's look at the second one, theorem 1.2. Finish that page. So this says every convergent sequence is bounded. Well, okay, we have to prove this. So we'll just let AN be a convergent sequence. Say that AN converges to the limit L as n goes to infinity. Okay? So AN is a convergent sequence and it has a limit L. So the picture kind of gives the idea of what to do here. And we're trying to prove that the sequence AN is bounded. We want to prove that there's a certain point in the number line and a certain second point in the number line, and that the sequence is all of the sequence from x1, every element after that is between those 2 points. And we can make use of the formal definition of convergence. Now, the formal definition of convergence speaks about talking about an epsilon, which gives you the radius around the limit. And the formal definition says, well, after some point, the sequence is wholly contained within. So that kind of tells you that, well, after some point, the sequence is bounded. Well, that's not quite what we want. We want to prove the whole sequence is bounded. But if we choose any radius epsilon, we'll be able to say, well, after a certain point, the sequence is bounded. But then the key idea is, I mean, let's say we just chose epsilon as 1. You can choose it as anything. Choose epsilon equal to 1, there's your interval. So we let epsilon equal to 1, then there exists capital N such that if n is greater than or equal to n, then the distance between xn minus L, the distance between xn and the limit L is strictly less. After this point, capital N, the sequence is bounded. So there's the first few points could be outside this interval. But the point is that there's only a finite number of them. So, xn plus 1, xn plus 2, and so on. All of these points have to be completely within the interval. That's what the formal definition of convergence is. Outside the interval, you might still have some points. Maybe x1 is down here, x2, x3 is down here, maybe x4 is down here. There might be a whole bunch of points outside the interval. But you can plot all of them, because they only go up to a certain point, only up to x capital N minus 1. There's only a finite number. Well, if there's only a finite number of them, then they can only get so far away from the interval. Just take the one that's furthest from the interval, and that gives you then your outer bound for the whole sequence. So what are we going to do? What we'll do is we'll let m be the maximum, and we're going to look at the maximum of a whole set of absolute values, x1, x2, all the way up as far as xn minus 1. Okay, so we're letting n be the maximum of all these absolute values. That will deal with the initial part of the sequence, but then from capital N on, we know the sequence lies completely within the interval. Then I just have to look at these two absolute values, L plus 1 and L minus 1. Now that's the point about that is it's just a finite set of numbers, so it has a maximum value. And we notice then that for all n bigger than or equal to 1, the absolute value of xn will be less than or equal to n, i.e. the sequence is bounded. Now, a key important step of this is that what we're taking here is a maximum of a finite set. Now, maximums of finite sets of numbers will always exist. Look through them all and you find the largest. A maximum of an infinite set might necessarily exist. Yeah, an infinite set of numbers, there may be no maximum, because it might be an unbounded set. There might be elements in there that are arbitrarily large. So you can't just prove this saying the sequence is bounded. You can't just say let capital M be the maximum element in the whole sequence, because the sequence mightn't have a maximum element. It's an infinite sequence. Infinite sets don't necessarily have to have a maximum value. But once you can reduce the focus down to just a finite set of numbers, x1, x2, xn minus 1, and then these last two, we're just looking at which one of these has the largest absolute value. We don't know which value is positive or negative, or we don't know the actual distribution of these points outside the interval. The key point is that set that I just took the maximum of, it's a finite set, so it does have a maximum, so I can name it and talk about it. Okay. So that's a proof that every convergent sequence is bounded. A corollary to this, what's a corollary? A corollary to a theorem is an interesting immediate result you get from the theorem. So you might not have seen that word. So a corollary, so this is an immediate interesting result or interesting consequence of the theorem. We've just proved that the theorem that every convergent sequence is bounded. But another way of looking, actually, it's more than a corollary. It's actually an alternative way of stating the theorem. It's an equivalent statement to the theorem, and that is that every unbounded sequence. Can an unbounded sequence be convergent? Well, no, because we've just proved that every convergent sequence is bounded. The sequence can't be unbounded and bounded. So one is the opposite of the other one. So every unbounded sequence we also know is divergent. So every unbounded sequence is divergent. It's not convergent. So it's more than a corollary, it's actually an equivalent statement to the theorem. But you can call it a corollary as well. Okay, so we've seen two ways then, the theorem 1.1 and theorem 1.2, two ways in which we can use the formal definition of convergence to prove these properties. Now the next property we want to come on with, and I'll just get you started with it, or just give you a clue to how it begins, will be the proof of the algebra of limits theorem. So this is 3 parts. First part talking about linear combinations, second about products, and third about quotients. So for theorem 1.4, part 1, we'll go through the formal proof of this on Thursday. Proof will have to, what it will say is, we will have to control the size. See, we're going to be looking at we're going to try to prove that the linear combination of sequence elements is converging to the linear combination of the limits. So we're going to have to show that this absolute value gets as small as we want. We want to show for every epsilon, this from a certain point on, this absolute value is less than epsilon. That's what I mean about controlling the size. So what we're going to want to do is to control the size of this absolute value of differences using the fact that we can control the size. We can control the size of the absolute value of A and the absolute value of Bn minus B as An converges to A and Bn converges to B as n goes to infinity. So we know, when we come into proving this, we'll know that the sequence An is convergent and that Bn is convergent to A and B respectively. So that means we know how to control the size of these two absolute values. Given any epsilon, we can find a point in the sequence after which these absolute values are as small as we want. Now, knowing that, we want to show how we can do the same thing for this absolute value of differences here. And it's not unreasonable to think that you can, except it's kind of complicated because we don't yet see An minus A. I mean, we see something like it, alpha An minus alpha A. We've got beta Bn minus beta B. But then they're added together before the absolute value is taken. So the proof will just be about how we carefully take our ability to control the size of these two absolute values and use that to control the size of this. So we'll see the details next time. Okay, so we'll prove the algebra of limits theorem next time. And then we should be able to tackle everything up to question 9 then in that first set of exercises 1.1. Okay, so I'll see you tomorrow afternoon.